previous class we discussed about the T-type topologies, right? So next we will discuss the other category, so that is unit-based topologies. So in this unit-based topologies, so the meaning is each unit, right? So that what we are going to study is itself a inverter. Each unit, so itself is inverter. For example, this is a unit-based topology. So this itself produce some certain number of levels. So this will produce certain number of levels. So this will produce certain number of levels. So here also this will produce certain number of levels. This one and this one. So all these things are produce certain number of levels, and we cannot extend this topology, right? We cannot directly extend this topology. So only possible way to extend this topology is to cascade different modules. Only possible way to extend these topologies is cascading. So we'll discuss one by one. Right. So previous class we discussed this already, right? So this is HSC unit. So this is HSC unit. So we already discussed that this the placement of the switches are wrong. So it should be opposite like this. Okay, the placement of the switches are wrong, right? So this is HSC unit. So we already discussed that. So each one or each HSC unit will produce 5 level if it is a symmetrical. If it is an asymmetrical, so it can produce up to 7 levels. If it is 1:2 ratio, so it can produce 7 levels in the output voltage. So we already discussed this. So if you want to extend this to higher level, so one way is to connect several modules in cascade. So that also we see in the previous class. So this HSC is a generally unit-based topology. So unit-based topology, that means each unit is a reduced switch count multi-level inverter. With that particular unit, so you can get some finite number of levels. The same example. So this is another one. So this topology looks like this. So this is a 5-level symmetrical topology. 5-level symmetrical topology. So here you have this H bridge. Here you have this H bridge and one chopper cell is connected here, and you have another DC source, right? So here, so up to here, if you are measuring the voltage from here to here, if you are measuring the voltage, so from here to here, so how much voltage it will appear? So there are two options. So that means we need to add these two voltages. So that means, so which switch we need to turn on? If we want to add these two voltage sources, so which switch we need to turn on?
S1.
If we turn on S1, right? So these two will be in series, so that you can get a voltage of 2 VDC if you assume that both are same. If you want only VDC, you need to turn on the switch S2. So that gives you, if you turn on S1, so it will gives you 2 VDC voltage. So for that, you need to turn on S2, right? So can you produce or can you get 0 voltage from this? Can you produce 0 voltage from this?
Yes, sir.
See, with this structure, can you get 0 voltage? So with this structure, so can you get 0 voltage?
Yes, sir.
Which switches we need to turn on?
S2, sir.
If you turn on S2, right? So that voltage is VDC2 only, right? If you turn on S2, so this voltage is VDC2. So for example, if you turn on this S2, right? If you turn on S2, so this voltage between here and here is VDC only, VDC2. Right. So with this unit, you cannot get a 0 voltage, right? You can get a 0 voltage here, this point. So you can get two voltages. So one is VDC and another one 2 VDC. So this will act as a polarity generator. This H bridge will act as a polarity generator. From this H bridge, right, so from this H bridge, in fact, we can actually convert this into 2 VDC to minus 2 VDC, including 0. So 0 can be obtained by operating any upper 2 or bottom 2 switches in the H bridge. Right. So this is how a 5 level can be obtained. So by using this this unit based topology. So this is another one. This is similar to this one. So but this is slightly different. Right. But it will this one is producing 9 levels. So this one is producing 9 levels. Right. So usually, so this is operating with VDC. Right. So this is VDC and this voltage is 2 VDC and this voltage is 2 VDC. So this voltage is VDC and this one, so 2 VDC and 2 VDC. So the voltages are so this is 2 VDC and this is VDC and this one is VDC, right? So therefore you can get 9 levels in the output voltage. You can get 9 levels in the output voltage. Okay, so ranging from 4 VDC to minus 4 VDC. So if you want 4 VDC, so which switches you need to turn on? Which switch actually you need to turn on to get 4 VDC in this? Which switches we need to turn on to get 4 VDC?
H1, H5, H3.
H1. Where is H1? This is H1, right?
Yes.
Okay. H1.
H5.
1 second. So H1. Yeah, and
H5, H3.
like this. H5. How H5 will turn on without H operating H6?
Starting from A, like H1, H5 and H4.
Starting from?
A point, sir. A point we can go through H1.
Yeah, we can go through this A, right?
Then H1, sir. Downwards.
Yeah, downwards.
Then
And we
H5,
do
sir.
two DC sources like this.
5.
Yeah, like this, right?
Yes, sir.
Yeah. So this will gives you this 4 VDC. Right. So this will gives you the 4 VDC. Similarly, you can also get minus 4 VDC with that. You can also get minus 4 VDC, or you can also get some intermediate levels. Right. So the good thing is, so here whatever this right. So these are rated for VDC, and this is also rated for VDC. Right. So these switches, right, this entire thing is 2 VDC, right? So this is equally sharing among these, right? So for example, this is turned on. If switch is on, so in that case, it's supposed to block 2 VDC voltage. So each switch, this switch must be rated for 2 VDC. The switch is also rated for 2 VDC. But whereas the other switches, this one or this one, are supposed to rated only for VDC. These switches and these switches are rated for VDC, and this switch, right? So this switch, in case of this bidirectional switch, so what is its blocking voltage in case of bidirectional switch? What is its maximum blocking voltage for this bidirectional switch? What is the maximum blocking voltage for this bidirectional switch? Right. If this is turned on, right? If this is on, so what is the voltage is supposed to block? This VC2, right? Clear? Or if this is turned on, it's supposed to block this voltage. So that means the maximum voltage, so that is blocking this bidirectional switch is VDC. We have two switches, right? So that means each switch is supposed to block VDC by 2. So these are the three unit-based topologies. Right. So we have other topologies. So here, this one. So this is another one. So this is another topology. This is visible.
Yes, sir.
I think I need to. I think it is right. It's clear. So this is another topology. So that is unit-based topology. This one will produce 9 levels. So this one will produce 9 levels. So it will be like this. So this one is like this. So we have these 3 DC sources and we have this additional unit. So we have this additional unit is connected here. This is the additional unit is connected here. So we'll discuss that. So why that additional unit is required. Right. So here, if you this entire thing, you have 4 DC sources, right? If you assume that, so all are VDC. If you assume that all are VDC, so you can actually get this 9 levels. If you assume that all are VDC, this actual voltage is supposed to be 4 VDC, right? So to obtain 4 VDC, so which switches you need to turn on? To get 4 VDC, so which switches you need to turn on?
S1, S2, S3, S7.
So S1, S2, S3 and S7, right? So if you want minus 4 VDC, which switches we need to turn on? Can we get minus 4 VDC from this? I think. Right. If you want VDC, which switches we need to turn on? If you want VDC, so which switches you need to turn on?
S5, S7.
S5, S7.
S5 and S7, right? Right. You know that, right? So we need to turn on this S5 and S7. For example, if this is not present, if this is not present, if this unit, whatever this additional unit is there, right? If that unit is not present, so in that case, right, you cannot access this middle one, right? You cannot access this middle one. Therefore, so in that case, you cannot access this middle one. That means if you want VDC only, right? So you cannot obtain VDC from that. So therefore, we have this additional unit, right? So whatever the voltage here, so that voltage, same voltage will represent this one, right? So because without this, you cannot get a VDC, right? Without this, you cannot get a VDC. So without using this, you cannot get a VDC level. Right? If you want to use this, it will be like this. You'll go like this and like this, right? So you'll go like this in this way, or you can directly go like this, right? So this is another path, and another path is straight away you have to connect all these DC sources. So this will gives you 3 VDC, and this gives you 2 VDC, and this gives you 0 if this is not present. Clear? So this gives you 3 VDC. If you go like this, it will gives you 3 VDC. If you go like this one gives you 2 VDC. You straight away go like this, so that gives you 0 voltage. But you cannot obtain this VDC voltage. So that means you cannot alone, right? you cannot alone access this one. You cannot alone access this voltage source, so that's why they connected. So here this additional module will increase the number of levels, and as well as it can produce the intermediate voltages, so that is VDC voltage, right? So once these voltages are obtained, so this A and 0, whatever this A and 0, right, so it is given to a polarity generator, so that will gives you the exact polarity, so that what you want, right? So this gives you the polarity generator. This is connected to a polarity generator. So next topology, yeah, right. If you want to use that, so one thing, if you want to extend it, this one to higher levels, if you want to extend this to higher levels, we need to duplicate this unit, right? So this unit is duplicated here, right? And you need to require only so one of this additional unit. So this is the additional unit, right? So this additional unit you require only one additional unit. So this additional unit is supposed to generate only VDC. Clear? So this is how we will increase the number of levels, and after that we need to connect to a polarity generator, so that will produce both positive and negative off cycles. Clear? So when you are increasing or when you are extending to higher levels, so no need to connect one more like this, so only one is enough. So one unit is enough. The purpose of this additional unit is to access this whatever, that means this point, right? So it can also works with, so 1:2:3 ratio. It can also work with 1:2:3 ratio. So when it is like this, so we need to make sure that, so this must be equal to 2 VDC. If this middle one is 2 VDC, and this extra unit must be 2 VDC, because we are not individually, or we are not individually accessing this, so middle one, right? So therefore it must be equal to 2 VDC. The additional one must be equal to 2 VDC. So we have other, right? So we have other topologies. So one is this E type, so envelope type. So this is E type or envelope type. So it requires 4 DC sources. So VDC, VDC, and this is 2 VDC, and this is also 2 VDC, right? So here, so this one, so can produce up to, this is 4 VDC, right? This is 2 VDC. That means here it can produce levels between 6 VDC to minus 6 VDC. 6 VDC to minus 6 VDC. And interesting thing is, it can generate both positive and negative off cycles. It means it can generate both positive and negative, and it doesn't require any polarity generator, right? So can anyone answer, so how to get 6 VDC and how to get minus 6 VDC? So which switches we need to turn on for 6 VDC and minus 6 VDC?
Sir, for 6 VDC, S1 and S4 and it is not visible, S5 I think.
Yeah, which switches need to turn on?
S1, S4 and S5.
S1, right? S1 and
S4
it is S4, yeah, S4
and S5, sir.
S1, S4, right?
S5, sir.
S5, yeah, exactly. So it will be, the path is like this. So that means it is plus 2, A is connected to positive plate, right? 2 VDC. Again, this is plus minus. So both are subtracting. This is minus VDC. I think you can see that polarities, right? So this is going from, this is plus minus. So this is also plus minus. And this is also plus minus. And this is also plus minus, right? So that means overall voltage is 6 VDC. The overall voltage is 6 VDC. Similarly, if you want only minus 6 VDC, which switches we need to turn on? Minus 6 VDC. Minus 6 VDC means this 0 must be connected to the negative, right? So this A must be connected to the negative plate, right? So that means we need to go like this, right? Like this, correct? Is this correct?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
So this will gives you the minus 6 VDC. Similarly, if you want only, right, if you want minus 5 VDC or plus 5 VDC, which switches we need to turn on?
Sir, S1, S4, and S8.
S1, one second. Minus 5
S1,
VDC, right? S1,
S4,
yeah, S4,
S4,
right, and
S8.
like this, right? So that means you are bypassing this VDC
Yes.
source. Okay, so that gives you the, right, so that gives you the 5 VDC, right? That gives you the 5 VDC. If you want 4 VDC, right, just connect like this. Okay, you just bypass this one like this. That gives you the 4 VDC, right? Clear? It's clear? If you want 3 VDC, 4 VDC is over, right? So 3 VDC. So how to get 3 VDC?
S1, S7, S5.
So I think so how to get 3 VDC? So from here S1 3 VDC, right?
S7,
S7, sir. S7, sir.
S7,
S7, yeah. S7,
S5.
S5 or S6.
yeah. S5, yeah. You can, I think, no, S5 or S6. See here, this is plus
S5,
minus, right?
S5
So
only.
this is plus S5
S5
only,
only,
right?
sir.
So not
S5
S7
only.
because the polarity is in the opposite direction, right? So this gives you 3 VDC, right? So this gives you 3 VDC. If it is only 2 VDC, straight away connect here, right? Straight away connect here. Clear? So if it is VDC, which switches we need to turn on? If it is VDC,
S2, S4, S8.
S2,
176.
S2,
Sir, S4.
S4, right? S2, S4, oh, sorry, this one, yeah. You can bypass here, right?
S8.
Okay, so this gives you the how much voltage? Plus VDC, right? If you want 0 voltage, so 0 voltage, I think is simply connect these 3 switches. I think that gives you 0 voltage, right? Correct? You're bypassing all the DC sources, right? So that gives you the 0 voltage. Clear?
Yes, sir.
Yes.
Clear?
Yes, sir.
So this is how we will get 6 VDC, starting from 6 VDC to minus 6 VDC. So with this unit itself is generating 13 levels, right? This unit itself is generating 13 levels, right? So you can also see its blocking voltages, right? You can also see the blocking voltages when this switch is conducting, right? For example, this switch is conducting. So what is the blocking voltage of this switch? S3. What is the blocking voltage of this switch S3?
3 VDC.
3 VDC, right? Both are in connect. So that means this is also rated for 3 VDC. And this switch, what is its blocking voltage? What is the blocking voltage for switch S1 and S2?
4 VDC.
sir.
4 VDC, right? If this is on, right? For example, this is on. So this point is connected here. That means 2 DC sources are in common series. So that means it's supposed to block 4 VDC. Agree? It's supposed to block 4 VDC. Right. So this switch S2 is also supposed to block 4 VDC. Right. So that means this is 3 VDC. So this is 3 VDC and this is 4 VDC and this is also 4 VDC. So what is the blocking voltage for this is S5. What is the blocking voltage for this is S5?
2 VDC.
If this is on, right? If this is on, right, there are two options are there. If this is on, so what is its blocking voltage is VDC, right? If this is off and this is also off, so what is its blocking voltage? 2 VDC, right? Agree? So this is 2 VDC and this is also 2 VDC. Right. So likewise, you can calculate the blocking voltage. So for this, if this is on, here are two options, right? So that means this blocking voltage is VDC only. Its blocking voltage is VDC. So likewise, we can calculate the blocking voltage for all the switches. So you can extend this one, right? So one of the way to extend this one is to series connection. You have one unit here, or this is series or cascade connection. You have one unit here and another unit here. So that means this entire unit, so it can produce up to 12 VDC to minus 12 VDC. So this is E type. Similarly, we have another one, so that is square T type. So that is ST type, square T type. So it is everything is same, whatever that circuit we discussed. So everything is same. So there are two variations. So one is this addition of this bidirectional switch. So earlier it is 2 VDC. So now it is 3 VDC. So both are changed to 3 VDC. That means we have 1:3 voltage ratio. So here there is no switch here, right? And this voltage is also 2 VDC and this is also 2 VDC. The change is here 3 VDC, 3 VDC, and we have this additional bidirectional switch. Right. So this additional bidirectional switch, because it is operating with 1:3 ratio, right? Somewhere you want to subtract this VDC and minus VDC. So that gives you then some support. That means it gives you the binary and trinary voltage ratios. Right. So therefore, this entire unit, this is 3 and 3, 6 plus 2n, right? So it will vary from 8 VDC to minus 8 VDC. So that means it will produce 17 levels. Right? So this can produce 17 levels. So you can increase the number of levels by cascading or the series connection. So whenever we have series connection, we have different voltage ratio. So here we have voltage ratio can maintain as 1:3 VDC, right? So inside this is 3 VDC and here, right? So here you may have different voltage ratio. You may keep 2 VDC and 6 VDC. Right. So inside that, the voltage ratio is 1:3. So inside this one, so this source and this source, it must be 1:3. Right. So here also it is 1:3 is maintained. So here also it is 1:3 maintained. But from this unit, this is assumed this is unit 1 and this is unit 2. So but we have asymmetry. This is 1:3 ratio. Right. So this is 1:3 ratio. So here also it is 1:3 ratio, but this voltage ratio is binary voltage ratio or 1:2 voltage ratio. So that means it will support both binary and trinary. We can also have this is 3 VDC and 9 VDC. So it can also work with 3 VDC and 9 VDC, the other unit. Right. So this is about the square T type. This is about the square T type. So we have other units also there, right? So we have this other switched capacitor, so units also there. So one of the unit is this one, right? So one of such unit is, right? So here, so next category is switched capacitor topologies. So the idea of this switched capacitor topologies is to reduce the requirement of DC sources. Right. So these topologies are aimed to reduce the requirement of DC sources. Right. So by carefully charging the capacitor voltages from the DC source, these topologies are actually derived. So how it look like? Right. So this is one of the switched capacitor unit. This is one of the switched capacitor unit. So it looks like this. So this is VDC, right? And here capacitor is connected here. Right. So this capacitor charged to the source voltage VDC. So based on the requirement, so this A and 0 will produce the, based on our requirement, so this A and 0 will produce the desired number of or the required output voltage. So now the question is, so how to charge this capacitor to VDC? So which switches we need to turn on to charge the capacitor to VDC? So which switch you need to turn on?
P, sir.
Right, if you turn on P, what will happen? If you turn on P, so what will happen?
So it will charge.
It will charge.
Capacitor C1 will charge.
So capacitor is C1 will charge. In other words, the capacitor will comes in parallel with the DC source, right? The capacitor will come in parallel with the DC source. So whatever that capacitor is having, right? So that means this capacitor is also now charged to VDC. Right. So now it look like having two DC sources. It look like having two DC sources. That means you are supposed to get 2 or 3 levels. If it is allowing 0 level, you will get 3 levels. Otherwise, you will get VDC level, 2 VDC level. Right. So how to get, so 2 VDC across A and 0? How to get 2 VDC across A and 0?
Turn on yes. Switches.
To turn on,
Which yes, sir.
if you turn
Which
on this
yes,
S, right? If you turn on this S, so what will happen? So both, means the capacitor and the DC sources will comes in series, right? So it will comes in series. So now you know the purpose of this diode, right? What is the purpose of this diode? What is the purpose of this diode?
To prevent the short circuit.
To prevent the discharging of capacitor, right? To prevent the discharging of capacitor, right? So therefore this diode is connected. So now it will produce 2 VDC. If you want only VDC, so which switch we need to turn on? If you want only VDC, which switch we need to turn on?
P.
P, sir.
P, right? If you turn on P, again what will happen? So whatever, see here there are two cases, right? So how this capacitor is usually self-balanced. So how it is self-balanced here? So when you are getting 2 VDC voltage, right? So what's happening is, right, both DC source is delivering power and this capacitor, both are in series, right? So both are delivering power, right? So both are delivering power. So obviously this is stiff source, right? This is stiff source. We assume that this is stiff source. So therefore its voltage will not reduce. But whereas this capacitor is not a stiff source, so therefore this capacitor voltage will be slightly reduced, right? So depending on the amount of the charge that is taking place, based on that, the capacitor voltage will be reduced. But when we are operating again with VDC level, so what's happening is the capacitor will comes into parallel with this DC source again, right? So that means whatever the energy or whatever the voltage lost, so when it is attempt to giving 2 VDC voltage, so that voltage is now recovered. Again this capacitor is charged to VDC. Again the capacitor is charged to VDC. So that's why all these things are self-balanced, right? So these capacitors are self-balanced. So that means this is giving two levels, 2 VDC level and 0 level. So can we get 0 voltage from this? Can we get 0 voltage? So can we get a 0 voltage from this? So you cannot get a 0 voltage, right? So with this, you cannot get a 0 voltage. So only way, right? So only way to get the 0 voltage is from the polarity rendered. So these are giving only 2 levels, but it is not giving, say, negative levels, right? So this can, so there are two ways to expand this one. So one is, so ignore this one just for time being. So here you are getting, right, so here and here you are getting 2 VDC and VDC, and this is giving to a polarity generator. So therefore the levels will change from VDC plus 2 VDC, VDC 0, minus VDC and minus 2 VDC. So this 0 level is obtained from the polarity generator, right? Clear? So this is how actually the switched capacitor topology will work. If you want to extend this, you can connect these two, right? You can actually connect these two into, right, in cascade. So this is cascade with this one. So this therefore this entire combination so can produce 9 levels starting from 4 VDC to minus 4 VDC. Again, when you are cascading that, you can have some different ratios. You can keep this one ratio, you can keep it 1:2 ratio or 1:3 ratios. So this is one way to extend this one. So other way is like this. So the other way is like this. You have only one polarity generator, but this switched capacitor units are duplicated here. The switched capacitor units are duplicated here. So like this, right? So now, right? So how much? What is the maximum voltage? So that can be obtained from this at these points. So what is the maximum voltage you can get?
4 VDC.
4 VDC, right? So that means this capacitor we can charge it to VDC. So this we can charge it to VDC, and this we can charge it to VDC. So how to charge all these three capacitors into VDC? So which switches we need to turn on?
P1, P2, P3.
All these switches, right? So this P1, P2, P3. So if you turn on, all the capacitor will comes in parallel with the DC source, right? All individual capacitor will comes into parallel with the DC source. So that means it can actually produce VDC. You can also 3 VDC, right? You can bypass any of the capacitor, or you can do VDC and VDC, right? Anyway, it will not produce 0 voltage, right? So all these unipolar voltages, so that is given to a polarity generator. So now this entire thing will produce 9 levels starting from 4 VDC to minus 4 VDC. Right. So this unit is also producing 9 levels. So this is also producing 9 levels. Clear? There is a difference here, right? So there is a difference here, right? What is the main difference? Can you compare these two topologies? Which is good one? Right. We have two options are there. Right. So can you compare these two? So which one is good? In previous class, someone has asked, right? So what is the significance of total standing voltage and this blocking voltage, right? So that will comes into picture now, right? So here, this is one option to increase the number of levels. So this is also producing 9 levels, and this is also producing 9 levels. So now we need to compare this, right? So if this is operating, so what is the blocking voltage of each switch here? What is the blocking voltage of each switch? What is the blocking voltage for this each switch?
VDC.
No, this switch, the switch in the polarity generator.
4 VDC.
4 VDC, right? So all these switches are rated for 4 VDC. So whereas here, what is the blocking voltage of this switch?
2 VDC.
2 VDC.
2 VDC.
2 VDC, right? So this is 2 VDC, 2 VDC, 2 VDC, right? So whereas what is the blocking voltage of this switch? This S and P switches, what is the blocking voltage of this one and this one?
VDC.
So VDC, right? So both are VDC. So what is the blocking voltage of this diode?
VDC only, sir.
So that is also VDC, right? So now we need to compare this one. So based on we have calculated this total standing voltages. So here you require only one DC source, but here you require two DC sources. You require two DC sources. So how many switches are required? 1, 2, 3. So you require 2 diodes and 4 switches. So here you require 3 diodes and 6 switches. Right. So here you require 2 DC sources, but here you require only 1 DC sources. So here all the switches here are supposed to rated for 2 VDC. So here also rated for 2 VDC, but these switches are supposed to rated for 4 VDC. Right. You can do some side-by-side comparisons by using this performance or by using these parameters. Clear? Right. So next one is this 3-phase reduced switch count multi-level inverter, that is 3-phase topologies. So far whatever we discussed, right? So those are actually drawn for single phase, except that neutral point pivoted. We have discussed NPP topology, right? So that is actually drawn for 3-phase. That is actually for 3-phase. We have this. If you want to extend this to 3 phases, right, this is one phase, this entire thing is for A phase. Similarly you have similar thing for B phase and C phase, right? So but whereas these topologies, so these topologies we cannot have a single phase units, so these topologies are directly for 3 phase. So this is another one. So this entire thing is a simple 2-level inverter, right? This entire thing is a simple 2-level inverter. So this is same, right? So it is 2-level inverter usually fed from a DC source. So that is its DC source. So what they did is just they opened here, right? So they opened this portion and connected these chopper cells. We already discussed, right? Half bridge or chopper cells. They're connected like this for A phase, B phase and for C phase. Right. If you want to increase this number of levels further, you have another unit like this, like this, like this. I think I have the diagram. Yeah, like this. You have another one. So another things are connected like this. Clear? Clear. So this is one topology. So this is directly extended from a 2-level inverter. So this topology is directly extended from 2-level inverter. So we have this voltages. We assume that this is voltage. This is A and 0 we are measuring. So these are the switches we need to turn on. If we want, this will produce 3 levels: 0 level, E level and 2E level. Right. Similar to the 2-level inverter, so you cannot directly analyze that. If you want to actually analyze that, so we need to measure VAB, VBC and VCA. You can only directly obtain the line voltages. You can directly obtain the line voltages. If you want only pole voltages, so if you assume this is the pole point, you can actually measure between VA and 0, VB and 0 and VC and 0, and these are the switches we need to turn on. If you want to measure voltage between A and 0, right, you are measuring voltage between A and 0, so you can get 0 voltage, right? So 0 voltage can be turned on. So if you turn on this switch directly, right, if you turn on, this is A phase, right? So 0 voltage, if you turn on directly here, so you can get 0 voltage, right? So if you want V voltage, right, so what we have to do is you need to turn on like this. That gives you VDC voltage. If you want 2 VDC voltage, you actually connect like this. So this gives you 2 VDC voltage. Is this correct? This is correct to obtain 2 VDC voltage between A and 0.
Yes.
Right. So you can bypass. Anyway, this source is common to all. You can bypass. If you want to connect this source, you can go like this. If you want to bypass, you can go like this. So that is simple. Right. So but you cannot analyze for this is for pole voltage, right? So similarly you have B phase pole voltage, so that will give you VB0. Similarly VC0. If you subtract any pole voltage, so that gives you the line voltage. Right. So with this, you can maximum, with this combination, you can actually get 5 levels starting from 2E to minus 2E. Starting from 2E to minus 2E. If you want to actually analyze that, so you need to consider this VAB and VC0. So all this will produce 5 levels. This is another 5 level. This is 5 level. So these are for line voltages. So it will generate 5 level in line voltage, not in phase voltage. It will generate only 3 voltages, 3 levels in the phase voltage or in the pole voltage. Right? It will generate only 3 levels in the pole voltage, but actually it is generating 5 levels in the line voltage. So I will give you so how to analyze that circuit. So it will be like this. The line voltages, so it will be in this form. Yeah. So these are the line voltages, so it will be in this form. So here you have, this 2 VDC level, so VDC level, so 0 level, minus 2 VDC, and this is minus VDC, and this is minus 2 VDC. Right? If for example, if this ABC voltage is minus 2 VDC, at the same time, right, you may have 0 value here in BC line voltage, and here at the same time you may have something like, I think it is better to see at this point. Right. So here, what is the voltage here? Minus VDC, right? ABC you have minus VDC voltage. At the same time, here you have minus 2 VDC. That means here VAB is plus VDC. At the same time, so VBC voltage is minus 2 VDC. So this is minus 2 VDC at the same time. And at the same time, its voltage is VCA is minus or plus VDC. Agree? I'm just looking at this portion. This one, this one, this one. Right? Clear? Actually, I'm measuring. Right. So this is the voltage scenario. Similarly, we have other conditions. If this is the case, so this is the one, and this is the one, and this is the one. Right. So based on that, so we can actually create the switching table. It will be something like this. Yeah. So this is the topology. So that what we discussed. Right. So this is Q1, Q3, Q5, Q2, Q4, Q6. That is the switches in actual 2-level inverter, and these are the additional units S1, S2, S3, S4, and S5, S6. And you can actually see here, right? So we have different conditions are there. So we have these different conditions are there: VAB, VBC, and VCA. So we have different voltages. You have E, minus 2E, and E. Right? If you are operating, if you are getting, right, so it must be satisfied, right? So if you are operating with this E, you are getting E, and you are getting minus 2E, and you are getting E in all the 3 phases, right? So that means one switching state. So for that, you need to operate these switches. So this is another switching state, so we need to operate these switches. So that means overall you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That means at least I think around 12 switching states are there. So based on these switching states, these are obtained. So you have doubt that how these things are obtained. This is minus E and minus E and 2E. So when you are operating this at this point, right? So we have divided this into 12 parts. I think each 30 degrees it is changing. Right? Each 30 degrees it is actually changing its magnitude. So this is one cycle. Each cycle is divided into 12 parts per 30 degrees. You remember that 180-degree mode of operation, right? So where we divided 60 degrees interval. So now we divided 30 degrees interval. So based on that, we have VAB, VPC, and VCA values are there for every 30 degrees. According to that, the switching states are actually defined. If you want, you can cross-verify this. If you want, you can cross-verify this by operating some appropriate switches. You can actually get the desired voltages. Clear? So this is about the 3-phase topologies. This is about the 3-phase topologies. So we have another one. So there is. So one of the switched capacitor topology. So that is worth mentioning. Yeah, this one. This is visible, right? This one.
Yes, sir.
Yeah. So this is another one. So this is one of the good topology, right? You have voltage source E here, right? So we have voltage source here. So this entire thing is at the tripler unit. So this entire thing is a tripler unit, right? So this is for polarity generator. So this is used for polarity generator. The operation is same. So here you are supposed to get, right? Here you are supposed to get 3 VDC level. So here the interesting thing is, here this is the circuit. This EC1 and EC2 are the two capacitors, right? EC1 and EC2 are the two capacitors. So these two capacitors are coming in parallel with the DC source. That means you have E here. So this is EC1 and this is EC2. So now, so which switches we need to turn on to achieve this? So which switches we need to turn on so that this DC source and the capacitors or individual capacitor will comes in parallel.
S1, S4.
Right. If you turn on this, for example, if you turn on this S4, right? If you turn on this S4, if it is like this, right? So both DC source and so capacitor in parallel, right? Agree? So both are in parallel, right? Clear? Similarly, so how these two things will be in parallel? If you turn on this one, right? So this one, so both are in parallel, right? So now which switches we need to turn on? Which switches you need to turn on? If you
S1
turn
and
on
S4.
S4, this EC1 will comes in parallel with the DC source. Similarly, if you turn on this S1, so this EC2 will comes into parallel with the DC source, right? So that means you are supposed to turn on S1 and S4, right? If you turn on this S1 and S4, so both capacitors are individually comes in parallel with the DC source. So now this capacitor, this is E voltage, right? So this is capacitor charged to E voltage and this is also charged to E voltage, right? So now you want to get 3 VDC across this one. That means you can get 3 VDC, 2 VDC, VDC and 0 voltage. So how to get 3 VDC here? How to get 3 VDC here? So that means this capacitors comes in parallel, right? Whenever you want, it will comes in parallel. Wherever it is feeding the load, so in that case, it is coming into series. How to connect these two capacitors and DC source, all three in series?
S3, S2,
S2 and S3.
Mhm.
S3 and S2.
S3 and S2, right? If you turn on, I think, so it will be like this. Is it correct? It will be like this, right?
Sir, above, sir.
Mhm.
Sir, E2, S2,
Is
and
it like this, right?
yes, sir. Yes, sir.
Yeah. So it is like this. So in that case, what will happen? So here we are charging the capacitors to E, that means the capacitors are coming in parallel, right? So whenever you want, the capacitor is coming in series, right? So now you are getting 3 VDC, right? If you want only 2 VDC, so if you want only 2 VDC, you need to, right? So you need to bypass any of the capacitor, right? If you want to only 2 VDC, you can simply turn on. If you turn off this S3, right? So obviously the diode will be in forward bias. So that means it is giving like this. So that gives you 2 VDC. Clear? If you want only VDC, what we have to do? Only VDC. Only VDC, what you will do?
No switch is turned on.
If you no switches, right? See here, if no switches are turned on, what will happen? It will be like this, right? The current will flow like this, right? But will you do that one? If no switches are turned on, so E is directly connected, right? So but when you're doing so, what will happen? The capacitors are never in self-balanced, right? If you're supposed to get E voltage, right? So in that case, you're supposed to turn on this S1 and S4, right? So that all the three will comes in parallel. So all the three sources will comes in parallel. So that means this capacitor, whatever that voltage that lost during the load transition, or that load, it is whenever it is feeding to the load, the capacitor voltage is reduced, right? So that means it will be recovered. Clear? If you want E voltage, you can, if you are not turned on any of switches, so automatically you can get E voltage. But you're not supposed to do that, right? So why we need to do why we're not supposed to do that? So these capacitors, it lost some voltages, right? Somehow we need to recover these capacitor voltages. The only way to recover capacitor voltages is to turn on the switches S1 and S4 so that the capacitors is recovered, and it will become, the entire unit will be self-balanced. This entire structure is self-balanced. Clear? Clear? So this is about one of this unit. Okay, so there are other units are there, so they are not worth mentioning, right? So this is about this entire thing.
Sir, there are too many topologies, sir. How we are going to remember all those, sir?
You no need to remember all those things, right? You have to see, no need to draw the topologies or no need to remember the topologies. You need to analyze the topologies, how they are actually working, right? The idea of discussing all the topologies here, how these topologies are, how this new topology is derived, and how to analyze the topologies. So that is what you are supposed to learn, right? How to compare different topologies, right? All those things you're supposed to learn. Okay, right? And one more thing I missed. So when you're discussing this switched capacitor, right? Here this is one. When you are discussing the switched capacitor especially, so there is one thing, so that is boosting or the voltage gain. There is one thing, so that is voltage gain. I think we already discussed that voltage gain is how much maximum output voltage you are getting, so that divided by total number of voltage of the steep DC sources. So in this topology, what is the voltage gain? What is the voltage gain of this topology?
3.
3 VDC.
3, right? So that's why it is known as triple R unit. So that is the voltage gain is 3 here. But the same thing we discussed here. One more thing, right? So what is the voltage gain of this one?
4.
4, right? So this voltage gain is 4. So in this case, what is the voltage gain?
2.
So it is actually 2, right? Yes, you're actually getting 4 VDC across this one, but you have 2 DC sources. So that means 2 VDC. So that is its voltage gain is 2. Our voltage boosting rate or voltage is 2. Here it is 4. So where here it is 2. Okay. Okay, you have any doubts? You have any doubts on this? You have any doubts? You can ask me.